In the last lesson that we looked at, we were exploring how exponential equations involve the application of population growth. In that case, we looked at a population of squirrels that was growing over time. In today's lesson, we're going to be looking at what we like to consider exponential decay, where we look at a population that shrinks over time. In this case, we've set up the situation where we have a forest population of approximately 16,384 birds. Every year, half of the population is dying off because of an infection. So let us set up our table, having already defined our variables. In this case, t will be the number of years, and capital B will represent the bird population. At 0 years, it is understood that the bird population will be 16,384. Since the bird population is going to die off by half in the course of 1 year, that will mean that 16,384 will not be the new population, but rather half of it will be left. So we will then have to multiply our number by 1, which will give us a bird population of 8,192. For year 2, that bird population will then again be cut in half. Instead of writing 8,192, we will represent 8,192 as 16,384 times 1/2. This represents the bird population of 8,192. This will then be multiplied again by 1/2, which will in turn give us a bird population of 4,096 birds. However, as in previous lessons, it is best to first simplify your notation. So we will simplify this notation as 16,384 times 1/2 to the second power, which will give us our bird population. As we progress to year 3, we will begin to notice that this same bird population of 16,384 is really being multiplied by 1/2 continuously. So, as in the previous year, the number of 16,384 times 1/2 times 1/2 is really the bird population of 4,096. That again will be multiplied by 1/2, which we can then simplify into 16,384 multiplied by 1/2 to the third power, which will give us a bird population of 2,048. As we begin to do the calculation for year 4, what we will begin to notice is the same structure that we did for calculating the virus population and calculating the squirrel population. In this case, we will again be multiplying 16,384 by 1/2 times 1/2 times 1/2. This number here represents the bird population of 2,048, which we will then multiply again by 1/2, as half of the bird population dies off every year. Let us now simplify this notation to 60,384 multiplied by 1/2 to the fourth power, which will give us a bird population of 1,024 birds. As in previous lessons, what we begin to see as a pattern is the significance of the year with the exponent. As you notice, where you see 3 years, you also see the exponent in your work. The same would apply for 1, and even though you may not see the number 1, it is represented as 1/2 to the first power. So we will also square this. Now that we have seen a pattern with regards to the number of years and the exponent that shows up on 1/2, we can now generalize this pattern and see if we have t number of years elapsed, then our population of birds represented as 16,384 would be multiplied by 1/2 raised to the t power. We can now generalize this pattern as an exponential equation, which we can now define as b equals 16,384 times 1/2 to the t power. And this will represent the bird population. If we would like to determine the bird population in 6 years, then we are now able to use our exponential equation that we defined as b equals 16,384 times 1/2 to the t power. Let us now let t represent 6, meaning the number of years that have elapsed since the original bird population. As you can see in our equation, we now rewrite it as b equals 16,384 times 1/2 raised to the 6th power, which will give us a bird population of 256. So in the course of 6 years, the bird population went from 16,384 birds to 256. So in conclusion, this exponential equation represents the bird population after t years, similar to what we've done in the past with the population of germs, the population of squirrels, and the population of birds that we have done today. What we need to take away from this lesson is that we continue to see a pattern where the initial population is being multiplied by a specific number that keeps repeating over a course of time. In this case, we were looking at years.